Have you ever really looked at the shirt on your back and wondered, how it actually made? I don't mean designed, I mean engineered. Well, today we're pulling back the curtain on one of the oldest, most important technologies in human history, weaving. Let's dive into this hidden world of threads and looms.
So let's start by basically deconstructing the very fabric you might be wearing right now. It seems so simple, doesn't it? But there is a really sophisticated process hiding in plain sight. And once you get it, it totally changes how you see everything from your favorite jeans to a massive ship's sail.
Because if you zoom way in, this is what you see. Every single piece of woven fabric boils down to this, a simple, elegant grid. It's just threads going over and under other threads. That's it. This fundamental structure is the entire secret behind a fabric's strength and its flexibility.
To put a formal definition on it then, weaving is the process of interlacing two sets of yarns at right angles. Now, that word, interlacing, is absolutely key here. We're not just talking about laying them on top of each other. Nope. This is a systematic integration that creates a stable, unified material from nothing but thread.
So, those two sets of threads, they have specific names and really important jobs. First up, you've got the warp threads. Think of these as the backbone of the fabric. They run lengthwise and they're held under a lot of tension, so they're usually stronger. Then you have the weft threads. These are the ones that do the traveling, crossing from side to side, going over and under the warp to actually create the fabric.
Okay, so how do we do this on a massive scale? That's where the loom comes in. The loom is the incredible machine that automates this whole thing. And at its heart, it's basically performing a simple but incredibly fast three-step dance. So let's break down those three main moves.
These are what we call the primary motions. Why primary? Because without them, you simply can't make fabric. It all comes down to shedding, picking, and beat up. Every single woven thing in the world is made using this exact sequence.
So step one, shedding, is all about creating an opening. The loom uses these frames called harnesses to lift up a specific set of those warp threads while leaving the others down. This separation creates a perfect V-shaped tunnel, and that tunnel has a name. It's called the shed.
Right. Once that shed is open, it's time for step two, picking. This is where the weft thread, sometimes called the pick, is shot through that tunnel all the way from one side of the loom to the other. And on modern looms, this happens at insane speeds. We're talking hundreds of times a minute, using things like projectiles, rapiers, or even powerful jets of air or water.
And the final primary motion is the beat up. It sounds aggressive, and it kind of is. After that weft thread zips across, this big comb-like tool called the reed swings forward and forcefully pushes, or beats, that new thread tightly against the edge of the fabric we've already woven. This action is what makes the cloth dense and stable.
Okay, so those three steps create one new line of fabric. But how does the loom keep going for thousands of meters without stopping? Well, that is thanks to the unsung heroes of the loom, the secondary motions. And there are two main ones you need to know about. On one end of the machine, you have the warp let-off. Think of it as the supply reel. It's constantly feeding fresh warp yarn into the action. Then, on the other end, you have the fabric take-up, which is like the collection reel, winding up the finished fabric as it's made. You can see here how the let-off at the back and the take-up at the front have to work in perfect harmony. Their whole job is to maintain constant tension on those threads, and that is absolutely critical. If that tension is off by even a little bit, the whole weave becomes uneven and flawed. And finally, there's even a third layer of automation, the auxiliary motions. These are basically the loom's built-in safety features. They're constantly monitoring everything. If a single warp or weft thread breaks, or if something gets stuck in the shed, these systems instantly shut the machine down to prevent a major defect from ruining the fabric. Pretty smart, right?
So we've covered the how, but now let's get to the really fun part, the why it matters. How does changing this mechanical process actually affect the fabric you see and feel? This is where the engineering gets super interesting.
Well, the simplest change you can make is the interlacing pattern itself. A plain weave, like in a basic cotton shirt, goes over one, under one. It has the most interlacements, which creates a strong but textured surface. A twill weave, which you definitely know from your jeans, has that classic diagonal pattern. It has fewer interlacements, making it smoother. And then you have satin, which has the fewest interlacements of all, creating these long floats where a thread just glides over many others. And that is what gives it that incredibly smooth, lustrous surface. But listen, the pattern is only half the story. The other huge factor is density.
literally how many threads you can pack into a square inch. And this, it turns out, is a massive factor in how a fabric feels and performs.
And this is the key insight from the research. It turns out that as you increase the density, as you pack more and more threads into the same space, you consistently make the fabric smoother. It makes sense, right? The yarns get compressed, all the little peaks and valleys in the weave get flattened out, and the whole surface just becomes less rough.
But what's really fascinating is how the different weaves respond to this. Just look at twill. It gets a whopping 46% smoother when you crank up the density. Plain weave also sees a big improvement. But satin? It's already so smooth to begin with that packing more threads in doesn't change its texture nearly as much.
And this leads to a wild, totally counterintuitive result. You'd think satin is always the smoothest fabric, right? Well, not necessarily. At extremely high densities, the structural stability of a twill weave actually lets it get smoother under pressure. Meanwhile, those long, unsupported floats in a satin weave can start to buckle and shift around, creating new little bumps. So believe it or not, a super dense twill can actually end up being smoother than a super dense satin. Mind-blowing.
So what does this all add up to? Well, when you put it all together, from that simple grid to the complex high-speed mechanics, you realize that fabric isn't just made. It's engineered with incredible, mind-boggling precision.
We've seen how that basic grid of warp and weft gets transformed by a highly coordinated dance of shedding, picking, and beating up. It's all managed by a sophisticated system of secondary and auxiliary motions. It really does prove that every piece of fabric is, in its own way, a tiny piece of technology.
Which really just leaves us with one final thought. The next time you pull on a t-shirt or a pair of jeans, are you going to see just cloth? Or are you going to see the intricate, high-speed engineering that turns simple threads into the fabric of our world? Think about it.